How you all doing? Are you shell-shocked from the quiz, or was it okay?
Shell-shocked.
Shell-shocked. All right. Well, I guess you probably saw the solutions online. No? You could have seen the solutions online if you wanted to. Because they exist and you might be spending some class time, I don't know whether it's worth going over any of this stuff. I'm happy to do it, but I think given that the midterm is just a couple of weeks away, perhaps we ought to press on. It's up to you, though. I'm here for you, so what's the verdict? Press on?
Press on.
Quiz? I'll give a dissenting opinion.
No.
No. Moving on from the quiz. All right. Okay. We are treading a similar path then to the single variable calculus, or to that we did in single variable calculus. I've mentioned this before about the parallels. This time we are going to have to talk about limits, and then continuity, and then derivatives. This is the same as what we did, but because it's multivariable, some aspects are a little more complicated. Then, of course, we move on to integration. So then we finish with the fundamental theorem of calculus, but of course all these things have versions and are a little bit more complicated. So I just want to, again, reiterate that we're kind of retracing the same paths that we've done before. So the new stuff is not conceptual always, but or at least not the same concepts, but more about how to extend other concepts. So with that philosophy out of the way, need to talk about domains and ranges of functions. There's not much different in a range in a sense, given that we might be, say, taking a function, instead of one variable, take two variables. So f of x, y, that's a real number. So it takes in two inputs, two different real numbers, and comes out with one output, one real number. Now, given this function, what is its domain? Well, it's going to be, instead of f of x has the domain some subset of the real line. But this thing has got to have its domain as some subset of the plane. Now, it turns out that the structure of sets in the plane is a little more complicated than the structure of sets on the line. So in order to say a little bit about the sort of domains that we're dealing with, we need some concepts. And so, although these are not fundamental to the course, you're expected to have an understanding of what an open set is versus a closed set, or neither. So every set is either open, closed, or possibly neither. That wasn't very grammatically well phrased, but anyway, never mind. A set is either open, closed, or not open nor closed. Now, that's one concept, and the other concept is bounded versus unbounded. And as I said, we're not going to do proofs with these, but you are expected to understand what the concepts mean. It's kind of hard to just examine and come up with specific questions, so they more or less come up along the way rather than being the focus of specific questions. So these are completely unrelated concepts, essentially. And it's easy to get them mixed up, so I kind of want to go through them. I'll start with the bounded versus unbounded, because it's a little simpler. A set is bounded, basically, if you can give it a hug. You can put your arms around it. Well, your arms don't really fit. But that set is bounded because I can take a big disk centered at the origin and enclose the whole set in that disk. So bounded sets can be trapped in a big enough disk. Of course, if the set was like this instead, that's still bounded, but not by the same circle. I'd have to take a bigger hug. So as long as your hug is big enough. I try to make math into a bit of a pleasant subject. Hugs. Doesn't really work, though, I admit. Anyway, so that's the idea. If a set is not bounded, in the sense that there's just no way you can get your arms around it, no matter how long they are, then it's unbounded. But unbounded doesn't mean it's the whole thing. here's an example of an unbounded set going on forever in those directions. It doesn't go on forever in every direction. It's not just the whole plane. But there's no way you can hug the whole thing. I mean, no matter how big it is, it just keeps on going in these directions. And they could be even crazier. I mean, you could just take a spiral that keeps on going and going. That would be unbounded. There's no way you can enclose it in a disk. All right, so that's just a concept. You can write it down mathematically, but I prefer just, at least for this, in this course, to have an intuition about it. So are there any questions about what a bounded or unbounded set means? All right. So you can see why they call it bounded, right? You put a bound, it cannot escape your grasp, your hug, sorry, not grasp. All right, so let's talk about open versus closed versus neither. So there's some idea that a set has a boundary. So if it's a bounded set, then it should be quite clear that the boundary of this set is the edge. Now, sets can actually be quite complicated, so the boundary is not necessarily so easy to see as in this case. But nevertheless, the idea of open is that the boundary, none of the boundary is in the set. That's the sort of naive idea, is that open, the boundary is there, but it doesn't actually belong to the set. Whereas closed, the idea is that all of the boundary belongs to the set. So, for example, if I take a circle and everything inside, including the circle, the boundary of this disk, including the edge, is, of course, in the set. So this one would be closed. Whereas if I just took the interior, so I'm kind of thinking of this as, say, the set of points whose absolute value is less than or equal to 1. Whereas here, the absolute value is less than 1. If I just take the points inside, then the boundary, none of the points in the boundary are in there. So I want to have the idea that the set is open. And of course, you could do some hodgepodge of the two. Say, it's hard to write down an equation for this, but if I take this and maybe just those points. So I could describe that as the points where absolute value of x is less than 1, union the set of points where x squared plus y squared equals 1, and x and y are both, say, greater than or equal to 0. So it's just it's the interior as well as just the first quadrant boundary. That's neither, because some of the boundary is in the set and some of the boundary is not. Okay, so that's the basic idea, but there's actually a more nice, I don't know about this, a more precise way to describe it. So here's a precise way to describe an open set, and that's going to be the most useful thing. Here's the precise way to describe it. Any point in the set has a little surrounding blob let's call it a ball or a disk entirely within the set. Well, what does that mean? Here's my open disk. None of the boundary is included. What I'm saying is you can pick any point inside. There is a little ball around it that is entirely within the big one, the actual set that you started with. What if you're very, very close to the edge? Never mind, you just take a very small ball. No matter how close you are to that edge, but you're never actually on it because the set doesn't contain the boundary, you can find a small enough ball that's entirely within your open set. Of course, the original set doesn't have to be round. It can be some weird blob like this, as long as it doesn't include the boundary, then no matter how close you are to the boundary, you can find a little ball centered at that point, a little surrounding ball that is entirely within the set. Why doesn't this work for, say, a closed ball like this? Because the point you choose, this is now in the set. And if you think about it, there's no little ball that you can draw around this that won't have some outside stuff in it. No matter how small you draw that little ball around here, you will pick up some of the stuff from the outside of the set. So that is not open. That is not open. Open, you have to be able to have this property. Okay, it's a subtle property, but it turns out to be quite useful. Because as we'll see when we do derivatives, for example, and I'm jumping ahead a little bit here, but the idea there is that you need a certain thing to be true, not just where you are, but nearby. What does nearby mean? Here I am. What's nearby to me? Well, I mean, maybe the table is nearby, but even if the property didn't hold there, say the property was that it was hot, and there was some air conditioner blowing over there, or a heater over here. Well, what do I mean by nearby? What I mean is some little ball around me. That's where it has to be true. How little? Well, it depends. As little as I like. But not just at the one point. It has to be true in a little ball. And that little ball is called a neighborhood very often, right? Again, trying to keep up the sort of cute, well, not cute, friendly. You know, we're talking about hugs, neighborhoods. It's all very community-based. All right. So that's pretty much what I want to say about open and closed. There is also a version of closed that has nothing to do with boundaries, but it's not really relevant. I don't want to get bogged down. Okay, when you say negative infinity to positive infinity, are you thinking on a line or are you thinking in the plane? So you mean the whole plane, or do you mean the line within the plane?
The whole plane.
The whole plane. So all x and y. So the question is this open? Well, first of all, is it bounded or unbounded? It's definitely unbounded, right? You can't possibly hug the whole plane. Now, as for whether it's open or closed, suppose I take a point in it and say, can you find a little disk that's contained within the shaded area? Well, yeah. In fact, you could take a really big disk and it would also work. So it's definitely open. As it turns out, it's also closed. It's also closed. There's very few sets which are both open and closed. That is one of them. Another one is the empty set. That's both open and closed. But that's pretty much it. So, another question.
So if the set doesn't have boundaries, does that mean that it contains them?
Yeah, well, I mean, this is getting on to, again, the realms of, we're going beyond the course. The fact of the matter is, if it's unbounded like this example that I gave here, the boundary you see here seems to be included in the set. So it turns out that's a closed set. So you don't have to worry about the boundary at infinity. I mean, the fact is, the boundary is this line that goes on forever and this line that goes forever. It contains it, so it's closed. If it was like this, that's an open set. If one of those was solid and the other one was not, it would be neither. All right? So it's only this one that seems to have no boundary. Every other set has some sort of boundary as far as we're concerned. There are some pretty funky sets you can write down where the boundary could be, say, a whole big set, even though the set was kind of not very full. But that's, I mean, I don't mean to dismiss it. This is actually where a lot of interesting math lies. But I've got to be practical here because you all want to do well in the midterm. So. All right, any other questions about these concepts? All right, so now that we have that idea, the question is, how do you find the domain of a function? Well, it's the same thing. To find the domain of a function, you want to just make sure, in principle, anything goes, anything is good, except for a few things that come up. For example, so regarding a domain, you cannot have a 0 on the denominator. 0 on denominator, or in the denominator, is bad. We all know that. Square root of a negative number, bad. Same goes for fourth roots, sixth roots, and so on. But not the cube root. You can take the cube root of a negative number, no problem. Also, you cannot take the logarithm of a negative number, or even log of 0. That's bad. You can take the square root of 0. You cannot take the logarithm of 0. So those are the most common bad things. Most of the other bad things reduce to this. So, for example, what is the domain of the function defined by f of xy is the fourth root of e to the x minus y? What would the domain of that be? Well, if the fourth root weren't there, everything would be fine. The domain would be the entire plane. But with the fourth root, we need this to be greater than or equal to 0. So we need e to the x minus y to be greater than or equal to 0, i.e. y less than or equal to e to the x. What does that region actually look like? Well, y equals e to the x is our well-known graph. This is y equals e to the x. So we've got to take one side or the other. And it should be fairly clear that it's the downside, but just to test, I mean, y equals 0. If I put y equals 0 and x equals 0, then 0 certainly is less than or equal to e to the 0, which is 1, yes. So the origin is in the set. And I know it's got to be one side of the thing, and just in case there was any confusion as to whether it's above or below, I just tested the origin and I said, yes, it's in the thing because 0, it is in the set because 0 is less than or equal to 1. So that's the actual region, including this boundary. So just for yocks, is the domain unbounded or bounded? Unbounded, yes. It goes on forever that way, and that way, and that way. There's no circle you can draw around it. So it'll just keep on going. How about open or closed? Is it open, or is it closed, or is it neither? Neither? Who thinks it's neither? Who thinks it's open? Who thinks it's closed? Who doesn't think? Good. Now, it is in fact closed. The boundary is right here. And it's in the set because of the less than or equal to. So this is a closed set.
But can't you find another point, for example, y is minus infinity, and then keep going with
There's no infinity. There's no infinity. It goes on forever, but there's no point at infinity as far as we're concerned. You cannot plug in infinity.
If you go below the x-axis, you can always find a point and then circle it, and then circle it, and circle it.
That's only to do with open. Closed, as far as we're concerned, the best definition is that the set contains its boundary. And I see the boundary is exactly this line. It separates the set from not the set. And it's in there. If it was y less than e to the x, it would be open. So it's a closed set, as it turns out. Again, though, the chances of actually being asked whether a set is open or closed, it just seems like we've got already too much other stuff to worry about. And one of those things is level sets. So this does sometimes get asked about and is a fairly important concept in the whole shebang. So the idea of a level set, suppose I have something like this. Z equals x squared plus 4y squared. That may as well have been on the quiz. That's a paraboloid, elliptical paraboloid, as we've seen. So it's going to look something like this. So here's x, here's y, here's z, and its intercepts here are 1/2 and minus 1/2, whereas the x is a little bit bigger at 1 and minus 1. And so we're going to get, well, those are not exactly, strictly speaking, intercepts, but if z equals 1, we get an ellipse like this. So I'm just trying to give myself a point of reference. So the idea is we have a paraboloid, or a parabola, in the yz direction, and a fatter parabola in the xy direction. And that's a pretty lousy sketch. But anyway, I'm not talking about sketches, I'm talking about level sets. The idea of a level set is that what you want to do is consider this graph and make a contour map of it. What do I mean by a contour map? I mean, suppose I chop the surface at any height. Let's just pick some height and chop the surface. It looks like an ellipse. If I chop it at a different height, I actually get a different ellipse, a smaller ellipse as it turns out. What I want to do is take all those ellipses in the planes and kind of push them all down into one plane. I want to push them all down into one plane. So think of it as cutting the thing. This is a little like a cheese thing. It's made out of cheese, and it's like a cheese bowl. And I cut it, and I get this little cheese ring. And I slice it and slice it and slice it, and then all the cheese just kind of collapses. So how do I know that the rings don't intersect? That's a big point. How do I know that as I push them down, the rings don't hit each other? The answer is, if I have z is some function, then above any point in the xy plane is just one z. So there's an unfettered, or there's an sort of a chart that you can push. As you push this cheese ring down, that point's going to go straight down and cannot hit another point because it's a function. There's not two values. Out of these curves that we've been sketching, hyperboloids and one sheet, they're not always functions. They're not always functions, so they don't necessarily have level sets. However, if I write z equals f of xy, then that's a surface that is a graph of a function of two variables, and so you can always do this trick. Now, what are the level sets in this case? Well, I mentioned that you always get an ellipse, and as we've seen, it's kind of twice as fat in the x direction as the y direction. So if I actually collapse it onto xy, one of the ellipses is going to be like this. It's a pretty bad ellipse, but it'll do. So that is the equation of x squared plus 4y squared equals 1. This is what happens if you cut this at a height of z equals 1. You get that ellipse after you drop the cheese ring down into the plane. And if you do this with all the different planes, you get all the different ellipses which are sort of similar to each other in the sense that this direction is twice as big as that direction. So these are the level sets of this. So conceptually then, the idea is to chop this thing up with parallel slices. They're parallel to the xy plane. See what you get in each case, but instead of drawing them at the correct height, you just draw them at a height of 0 in the plane. Another way of looking at it is that all these different curves are the curves x squared plus 4y squared equals c, for some number c. How do you know which number c? It's all of them. You pick c equals 1, you get this one. You pick c equals 2, you get a bigger one. What about c equals 0? You get the origin. That's c equals 0. Because if c equals 0, x squared plus 4y squared equals 0. The only solution is x and y both 0. So basically, c cannot be negative. You could set it as negative, it makes no contribution. And together they actually in this case flesh out the whole space. So every point is on some level curve of this. That doesn't always have to happen. For example, if instead of a paraboloid I had something which had asymptotes in a way, like became quite vertical and never busted out, then the level sets may actually be bounded, the entire collection. All right. So we understand, at least in principle, what these things are. Just on Blackboard, and it's not a particularly difficult thing. We should take a look. So here's a function of two variables. F of xy is 1 over 16 minus x squared minus y squared. And the point is to try to find, in this case, the domain, the range We're looking for the level sets. We're looking for the boundary of the domain. And you want to know whether the domain is open or closed, bounded or unbounded. I've used quite a lot of abbreviations there. All right, well, we kind of know how to do this. What could perhaps the domain be? Well, what's bad? What can we not tolerate? The denominator cannot be 0. So the domain, we want 16 minus x squared minus y squared not to be 0, i.e. x squared plus y squared should not be 16. Well, what is x squared plus y squared equals 16 as a curve in the plane? It's the circle, center 0, the origin, radius 4. But that's exactly what we don't want. So these are the points that are illegal, but everything else, inside and out, is in the domain. So it's almost everywhere. It's almost the entire plane. But we have to cut out this thin little ring. In fact, it's not just thin, it's got no thickness at all, but it's nevertheless the non-allowed set. So that's the domain. How about the range? Well, the range, you know, it's kind of a pain to find in the one variable thing, and it's equally a pain to find in two variables. You kind of just have to ask, what numbers could I possibly get out of that? What numbers could I possibly get? Well, what numbers could you possibly get out of 16 minus x squared minus y squared? What numbers can't you get? What numbers can you get? Does anyone have any ideas about this? Yeah, up the back.
Can't get anything greater than 16.
Yeah, but you can get anything less than or equal to 16. Right? That's for sure. You can get anything less than or equal to 16. You could get negative numbers as well, right? Just choose x is really big and y is 0, say, or both of them really big, and you'll get negative numbers. Could be negative. So what about 1 over 16 minus x squared minus y squared? That's got to be greater than or equal to 1/16. How do I know greater than or equal to? Because I took reciprocal, so I switched that. Is that actually correct? Is that necessarily true? Who thinks it's true? Who thinks it's false? Okay, why do you think it's false? You don't have to answer if you don't want to. Okay, someone who thinks it's false and has a conviction as to why. Okay, go ahead. It can be negative, right. So the problem is, if one side is negative, then this thing is not correct. So you've got to notice that if this is negative, then surely its reciprocal is negative. So if 16 minus x squared minus y squared can be any number less than 0, in fact, any number, then its reciprocal can actually be any negative number as well. Can be any negative number. So, in fact, the range is minus infinity up to 0, union 1/16 to infinity. So you can have any number that is 1/16 or more, or any negative number. It's a bit subtle, but if you think about it, just plug in, say, x squared, and you can always even just set y squared equals 0, and you'll get the same range. So that reduces it to a one variable problem. All right, any question about the range? I agree it's a bit messy, but that's how these things work. Notice, by the way, that the domain is two-dimensional, but the range is only one-dimensional. That's because we have a function of two variables that spits out one number. That's two variables to one variable. Domain is 2, the range is 1. How about the level sets? Well, to find the level sets, we set 1 over 16 minus x squared minus y squared equals some constant. So the level sets are equal to this for some constant. So this means, we'll try to permute this around, 1 over c is equal to 16 minus x squared minus y squared. In other words, x squared plus y squared equals 16 minus 1 over c. And we don't say anything about c. C can be any number. Of course, it can't actually be 0, because if it's 0, then you have no solution. You can't solve this equals 0. You'll get 1 over 0. So this has got to be okay for any c not equal to 0. But that means that you can have any number here. Any number here except for 16. If c is constant, then you get x squared plus y squared is some other constant. So I'm going to just call this c prime, where c prime is just some other number. Maybe I'll call it c1. Not a derivative, it's a c1. c1 equals 16 minus 1 over c, i.e. c1 equals any number but 16. So the level sets are just circles. Over here, except for the one that's not allowed, which is not a level set, because it's not in the domain. So describe the level sets, circles centered at the origin, except for the one of radius 4. It's pretty straightforward. All right, so we've almost finished. What's the boundary of the domain? Does anyone want to just say what the boundary is? It's the entire set except for this circle. What's the boundary of it? It's a sort of weird set, but what's the only thing the boundary could be? It's that circle. The boundary is this circle. Well, exactly. It's this circle that's missing. I mean, we have to ask ourselves, what do we mean by a boundary point anyway? That's a fairly technical sort of definition. So I don't know if it's absolutely obvious to you, or it could be even clear, given that we haven't really said what a boundary means, that that should be the boundary of this set. But nevertheless it is. It's basically all the points that are either in the set, but very close to the edge, in the sense that there are parts around it that are not. So in this set, that's not in the boundary, because you can find a little disk. This is in the boundary because there's no disk that's entirely within. So it goes back to that same sort of definition. So these points are on the boundary because they're not in the set, and yet any disk picks up bits in the set. This is on the boundary because I can draw a disk that is separate from the set. So the distinction between exterior, interior, and boundary comes down to this. If it's in the interior, you can draw a little disk that's entirely contained within the set. If it's in the exterior, you can draw a little disk that's entirely contained outside the set. But the boundary are the points where every disk contains some point that's in the set and some points that are out of the set. So in this case, this is on the boundary because it's not in the set, but every little disk contains some points which are inside and some points which are outside, namely that little arc. So that's why that's the boundary. Question up the back.
What if C is a very small number down there?
What if C over here is a very small number?
Like x squared plus y squared equals 16 minus 1 over c.
Yeah. Okay, so suppose when you say very small, do you mean a tiny positive number?
Yeah.
All right. So if C is a very tiny positive number, then what happens? You will get 1% of it will be huge, and therefore this C1 will be negative. Well, that's okay. The level set doesn't exist then. Right? If C1 is negative, you get x squared plus y squared equals some negative number.
But then you said any number but 16, and you can't have square added together to be a negative number.
Well, right. I mean, so you're asking me, is that a level set? And it's a matter of definition as to whether x squared plus y squared equals minus 1 is a level set. You could say no because it doesn't exist, and I could say no because it doesn't exist. It's not screwing us up at all because it's not in the picture. So in some sense, technically, okay, it's not a level set because there's nothing. But in another sense, yes, it is a level set because anything of this form is a level set. It just happens to be the empty set. So I don't want to argue whether nothing is something or something is nothing, or whether I have nothing to say about it or otherwise. Anyway, so you get the idea. But yeah, no, it's a good observation. There are values of C for which the level set corresponding to that may be empty, in which case it's not really a level set. All right? Okay, so now you have an idea of what the boundary is. Okay, again, the reason this is the boundary is because if I put a point on it and I draw a little disk around it, I pick up points which are both in the set and not in the set. The points that are in the set are most of them, everything in the inside circle and outside the circle, but I cannot avoid picking up some points on the outside of the set, namely the dashed circle. So that's the boundary, okay? It's the circle there, x squared plus y squared equals 16. So now I ask you this, is the domain open, closed, or neither? Who thinks that it's open? Gee, the conviction, the conviction. I don't think we had this on camera, but out of a fairly full room, I got maybe one definite hand and a lot of just, so either you don't know or you just don't care. No, I mean, okay, let's try again. Who thinks it's open? All right. Who thinks it's closed? All right. Who thinks it's not? All right. Sorry? This is not democracy. This is just a straw poll. Okay, the answer is that it's open. The definition of open is, as far as you're concerned, the easiest way to tell is that the boundary is not in the set. What is the boundary of this? We just discussed it. It's that interior circle. X squared plus y squared equals 16. Is it in the set or is it not in the set? It's partly in the set. No, none of that boundary is in the set. Therefore, the set is open. So none of the boundary x squared plus y squared equals 16 is in the set, so it's open. Another way of looking at it is this. Here's the set. Pick any point. So here's the set. Not that. Pick any point in the set. I don't know. It could be here. You can draw a little thing that avoids this bad part. You want to be able to stay away from the bad part. So it's open. Is it bounded or is it unbounded? The domain. Who thinks it's bounded? Who thinks it's unbounded? Okay, good. It is unbounded because it goes on forever. It's actually the parts outside the circle which are unbounded. Okay, so we've finished the problem in gory detail. Any questions about it? Yes?
You can say what the boundary of a set is even if it doesn't have a boundary.
It does have a boundary.
But it's open and not has a boundary.
Oh yes, open sets can have boundaries. I know what you mean. It doesn't look like this set is a boundary. It doesn't look like the set has a boundary. In the normal sense of the word, it's a fence that neither keeps you in nor out. But it's still a fence. It's still a fence, and it is a boundary. Yeah. What would the boundary of this set be? So it's not that circle, but everything inside that or outside that. What would the boundary of such a set be? Well, it would be this circle and this circle. And as it happens, because I use dotted lines, none of the boundary is in the set, and that would be open. Okay, so that case, I think you could agree that these things fence the set around. Now what happens if I bring them together? I get that picture there. So it does sort of make sense that that would be a boundary, even in layman's terms, as it turns out. All right, here's another quick level set question with no other parts. It just says, find an equation for the level curve of f of xy And here's a bizarre function. The integral from x to y dt over 1 plus t squared through, passing through, minus root 2, comma root 2. Well, it's such a bizarre function. The reason it's bizarre is given an integral. But I propose that we immediately reduce it to a not an integral, because we can actually work it out from Math 103, or the equivalent. It's just inverse tan t evaluated between x and y, so it's inverse tan y minus inverse tan x. Why didn't they say so in the first place? I don't know. That's what the function is. So what does a level set of that function look like? Well, all the level sets are given by f of xy is a constant for some c. So they carve out the plane in the form inverse tan y minus inverse tan x equals c. So for different values of c, we get different curves that don't intersect, and they are the level sets. We want one of those curves. We want the one passing through minus root 2, comma root 2. Well, if we plug in x equals minus root 2 and y equals root 2, we get inverse tan root 2 minus inverse tan minus root 2 equals c. Well, that's told us what c is. The only thing we should do is tidy it up. Does anyone know whether tan is an odd or even function, or neither? You remember? Yeah, tan is odd. Sine is also odd. Cosine's the even one. So how about inverse tan? Also odd. So what you really want to be able to do is say, inverse tan minus root 2, the minus pops out. And so we actually get a plus here. These two cancel out and give us a plus. And so c is equal to 2 inverse tan root 2. And I don't think I can simplify it much more than that. So the curve we're looking for, we want inverse tan y minus inverse tan x equals 2 inverse tan root 2. Sorry to squish it down like that. And that's it. Maybe you can make y the subject, solve for y by throwing the inverse tan x on the outside and taking tan both sides, but I think that's all we need. All right? So basically all that's required is to know that level set means set something equals c, and beware that c could in principle be anything. Now, I might just comment that it also works for functions of 3 variables, of course, but instead of the level sets being curves in the plane, they're actually surfaces in space. So the level sets of this, let f of x, y, z now be a function of 3 variables. X squared plus 2y squared, actually let's do 4y squared plus 9z squared. I can't graph that because it doesn't equal anything. But if I take the level sets, our x squared plus 4y squared plus 9z squared equals c for different values of c, what do these things look like? Well, if c were equal to 0, you just get the origin. If c equals 1, you get what? An ellipsoid. So c equals 1, you get an ellipsoid going through 1, a half, a third, and it's negative, so it's something like that. As c gets bigger, you get bigger ellipsoids. Okay, those are the level surfaces of this. A more interesting example is something like this. X squared plus y squared minus z squared. Let's say that's f of xy, or g of xyz, rather. So the level sets are x squared plus y squared minus z squared equals c for some c. And as we discussed, when c equals 0, you get a cone. When c equals positive number, you get a hyperboloid of 1 sheet. Whereas when c equals a negative number, you get a hyperboloid of 2 sheets. So as c varies over everything, you get the sort of picture that we already looked at. There's a cone, actually a circular cone, and then you get all these different hyperboloids of revolution. And that kind of fleshes out all the space outside the cone, so you get lots and lots of them. They're all sort of funnels within funnels, except they're not actually funnels, they kind of widen out again. And then you have all these little bowls, bowls within bowls. And it's kind of weird, but together all these surfaces flesh out the entire space. So depending on the value of c, you get all these different level sets.
Looking at something like that, how would you know whether it was closed or open or unbounded or bounded?
Or unbounded, bounded. Okay, well these particular sets here are all surfaces. It turns out that a surface itself just... Okay, so in 2 dimensions, any curve like this, just the curve, not the interior. So I'm not talking about the inside, I'm just talking about the curve. Yep, just the outside. So that is all boundary. It's got no interior. So it is its own boundary. So does it contain its boundary? And the answer is yes, because it is its own boundary, so it's closed. So any curve by itself, without worrying about the interior, is going to be closed. It wouldn't be closed if it, however, did this. Because now the boundary is the curve plus the n bits.
So are the surfaces also then?
The surfaces...
also their own boundary?
Yes, so in 3 dimensions, a surface is its own boundary. Unless, of course, it just sort of stops. If there's the top rim of the bowl, then if that rim is like the boundary of the surface. But in 3 dimensions, now you have to ask, is the rim included or is it empty? So it gets a little bit technical. But in this case, all these surfaces as 3-dimensional objects are closed, but they're all unbounded. This is closed as a 2-dimensional object, and it's bounded. If I take any curve like this without the endpoints, it's neither open nor closed. But if I throw in the endpoints, it becomes closed. Anyway, again, it gets a little technical. All right. Another question.
It takes up all of space.
Yeah, actually, I believe that for different values of c, these give you a cone, and then 2 sheet things and 1 sheet things, and between all of them, it just fills out the entire space.
Why wouldn't it be open and closed?
Well, the union of all of them is everything, so it's open and closed. But any one of the individual surfaces by themselves is a closed set, because it's just a boundary. All right? Any other questions? Yes? Probably not. You don't need to know that. I don't know. It's on a need-to-know basis. All right, let's move on. Let's move on. Limits. We've got to spend some time talking about limits. Now, there is this sort of need to know, because you've done it to some extent in class, I kind of want to avoid the epsilons and deltas here, and I want to just, again, tell you what it means practically, and I also want to show you some examples, a bunch of examples. Okay, so primarily I want to talk about limits in 2 dimensions. If I have a function, f of x, y, and I want to say that it goes to L as xy goes to x0, y0. That is the same thing as saying limit as xy approaches some point x0, y0 of f of x equals L. These 2 things mean the same thing, but what does it actually mean? I'm trying to do an analog of what we did in 1 dimension, which said limit as x goes to a. This meant that when x was very close to a, f of x is very close to L. Here, instead of x goes to a, I now have a pair of variables, x, y, going to some x0, y0. So remember how we had a left-hand limit and a right-hand limit? If you're dealing with a line like this, and here's a point A, and you want to get close to it, so creep up on it, but not actually get there, then the two really coherent ways you can get there are from the right or from the left. Okay? It's a little more complicated in 2 dimensions. If you're getting snuck up on, and you're in a really narrow corridor, they're either coming from that way or from that way. But if you're just standing in the middle of a field, you could get snuck on from any direction, right? So this is why we've got to be a little more careful with two dimensions. So if here's our plane, and here's our magic point where we're standing, x0, y0, there's not just a right and a left, there's all the directions. So we have to be able to take care of that. But it's even worse. You don't necessarily even have to get snuck up on by someone coming straight at you. They might just kind of do this windy path. So we actually have to deal with every path, even a curvy one. And sometimes it makes a difference, as we'll see. So what this means effectively is that for any path, as xy gets closer, so in any path going along, if you look at the function values along that path, they get very close to L. So this has to be, basically this means as along any path. Not just even a line. Along any path that stops right near x0, y0. In fact, it stops at it, but it never quite gets there. You know about these asymptotic sort of ideas. And so I kind of want the values of f of x to be close to L. That's what I need for a limit. Again, the precise definition involves epsilons and deltas. And the idea is you can cover your bases with any path by taking disks around and insisting that it's really close to L here. Oh, now it's even closer to L. Now it's even closer to L. So disks surrounding you will cover any approach. So that's where the epsilons and deltas come in. But practically speaking, that is a good intuitive sort of definition. So, to see what we're up against here, let's look at a few examples. By the way, I should have said one thing about this. It's possible that you're dealing with a point and the domain might be, say, everything but this line and this line. Then the paths, any path's okay as long as it doesn't cross somewhere out of the domain. So if I'm standing in a field, but I'm kind of on the wedge of some like hay bale or something like that, then the person sneaking up on me cannot walk through the hay bale, but they can go any other way, and the limit is still fine. Okay, so just because I may have these bad points near me where I'm standing here, it doesn't invalidate the possibility of having a limit. As if there are no paths, so that the domain is, say, everything outside this circle, I can't have a limit here. There has to be at least one path. I mean, come on. Otherwise it doesn't make any sense. But anyway, so that can become a little bit relevant occasionally. All right. So let's look at some examples. Consider this. What is the limit as xy goes to the point 7,5 of this? X squared minus 7x plus y squared minus 10y minus 25. No, this is supposed to be a minus y squared there. And this is supposed to be a plus 10y. And over x minus y minus 2. Okay, as usual with any limit like this, the first thing you ought to do is just plug in. So try x equals 7 and y equals 5. By the way, this means x goes to 7 and y goes to 5. It does not mean x goes to 5 and y goes to 7. This is observed here. So I plug this in first. And what do you get? You get 7 squared minus 7 times 7. So you get 49 minus 49 minus 25 plus 50 minus 25 over 7 minus 5 minus 2. And if you work this out, you do get our old friend 0 over 0. Okay, so it is an indeterminate form. If it is not an indeterminate form and you get, say, 0 over 3, well, then the limit is just 0. If you get 3 over 0, then the limit probably doesn't exist. Or if it does, it's infinity. But that can be pretty messy, because instead of just having a right hand and a left hand, remember, you've got all these weird paths. But anyway, in this case, we have a 0 over 0. And now, our tactic in one variable was to try to factor the top. This seems a little bit hopeless. This seems a little bit hopeless. So we ought to just see, as a reality check, whether this thing exists over different paths. Now, there are paths and there are paths, I have to tell you, but there are always two really easy paths. Okay? One path is along the y-axis, and the other path is along the x-axis. Those are the two easiest paths to check. So we're going to try horsing around. Since I don't fancy trying to factor that, because it's two variables, try the path y equals 0. Now that means that y equals 5 rather. I've got the point 7, 5 as my limit point here. And so when I said the x-axis and the y-axis, maybe I also mean perhaps parallel to them. So y equals 5 means I'm approaching from here or from here. So I'm going to try those paths. That's the line y equals 5. That's one way of getting to the point 7, 5. So if I try that, then the limit that I get, I need to look at the limit as just x goes to 7, because I'm going to set y equals 5, of x squared minus 7x minus 5 squared plus 10 times 5 minus 25 over x minus 5 plus minus 2. So I've simply set y equals 5. And now this is cancels, because this is minus 50 plus 50. And so this actually looks like the limit as x goes to 7 of x squared minus 7x over x minus 7. That's a one variable limit, and if you think about it, you can factor the top into x minus 7 over x minus 7. They cancel, and you just plug in x equals 7. So the limit, as you creep up this way or this way, either side, then this quantity goes to 7. How about if you creep up on it vertically? So this one is x equals 7. So we do exactly the same thing, but instead we set x equals 7, and then we have the limit as y goes to 5, since we've frozen x, of 7 squared minus 7 times 7 minus y squared plus 10y minus 25 all over 7 minus y minus 2. So this is 49 minus 49. And if I simplify and just for yokes multiply the top and bottom by minus 1, just to simplify it a little bit more, you'll find you get y squared minus 10y plus 25 over y minus 5. All right, that's again 0 over 0, but we can factor the top. The top is y minus 5 all squared. This is y minus 5 all squared. So actually we'll cancel out, and it works out to be the limit as y goes to 5 of y minus 5, which is 0. Okay, so as we approach from this direction or this direction, the function gets very close to 0. As we approach from this direction, the function gets very close to 7. What does that mean? That's just two different paths, and we got two different limits. the limit from all different directions does not exist. It has to be the same number from every path. And we have just found two paths, the first two that we even tried, that gave different limits. So two paths give different limits. Seven and 0. So the main limit does not exist. Which main limit? The one we started with here. This does not exist. So you see, it's quite a stringent condition to have it from every path. You would think that it should just work, but as you see, there are examples where it doesn't. Now, the situation can be even weirder. Yes, it's true. Consider this. Suppose you take this. This is something similar to the textbook, although I don't think it explains it properly. F of x, let's not worry about f. Well, yeah, let's not worry about f of x. Let's just do this. The limit as x and y, or x comma y, goes to the origin of this quantity x squared y over x to the fourth plus y squared. All right, so suppose we try to find that. Now, we could try the path y equals 0. So we get the limit as x goes to 0. Well, when y is 0, we get 0 over x to the fourth. So that limit is just 0. You could try x equals 0, but that's also 0. There's an extra 0 there. So it's the same as you go along a horizontal path or a vertical path. What about along another line path but some other line? How do you describe some line through the origin? Y equals mx or ca. I'll call it y equals mx because I'm used to that, y equals mx plus b. How about along y equals mx? Well, this is now the limit just along that path of x comma mx goes to 0 of x squared times y is mx all over x to the fourth plus mx all squared. Well, I mean, m is a constant. M is fixed. It's just some number. So what does this even mean? That's going to happen as x goes to 0. That's the only way you can get the point along the line x comma mx to go to 0 is when the x coordinate also goes to 0. Then the y coordinate automatically goes to 0. So this is basically a one-dimensional limit as x just goes to 0. That's good enough. If x goes to 0, mx also goes to 0. And you get mx cubed over x to the fourth plus m squared x squared. And we can cancel out a factor of x squared. And you get the limit as x goes to 0 of mx over x squared plus m squared. This is no longer a 0 over 0. Remember, m is a fixed number. And so if you plug in 0, you're okay. You get 0 over m squared, and you get 0. So as you go along any line towards the origin, the limit is 0. So you must be pretty sorely tempted to conclude that the limit is in fact 0. But alas, it is not. Because remember, I said you didn't have to go along lines. You have to be able to deal with any approach path. And in this case, if you go along the approach path like this, consider the approach y equals x squared. So that means that instead you're really sneaking up to the origin like this. Or from this side. if you do this, you have the limit as x comma x squared goes to 0, 0 of x squared times y is x squared over x to the 4th plus x squared all squared. And if you work this out, this is x to the 4th over x to the 4th, which is a half. So no matter what this is 1/2. However, if you go along y equals minus x squared, which is this, so you're approaching from this side, and you plug it in, then you get the limit as x minus x squared goes to 0 of x squared times y is minus x squared over x to the 4th plus minus x squared all squared. And if you work it out, you get minus x to the 4th over 2x to the 4th, and so that limit is minus a half. So actually, we didn't even need to do both of these. This one is enough, because all the limit gave us 0, but this one quadratic path gave us a half. But just to hammer in the point, I tried a different quadratic path and I got minus a half. In fact, all the different quadratic paths give you different limits. So the limit, again, does not exist, but in a more subtle way. And that's kind of hard to tell. That is kind of hard to tell. It's going to be the sort of thing where you might just recognize it, but, you know, I can't immunize you against every attack of this sort in terms of a midterm problem like this. All I can say is try quadratic paths. You might get lucky if all the linear paths come out as 0. A question up the back first. Is there any way you can use this method to conclusively prove that a limit does exist? The answer is no, because you cannot possibly check every path. There's just too many of them. You're going to check the quadratics, the cubics, plus the sine, plus, you know, there's many different approach paths. So this method is not the ideal one. Got a question here.
Yeah, how do we prove that?
I'll give you a couple of examples coming up. I prefer to be negative first, but then I'm going to get more positive as my outlook improves. Question up the front.
We did a Taylor series example in class.
You saw an example in class?
We proved something for
With
Taylor series.
With Taylor series, right. So there are ways and means of proving that limits do exist. But, well, yes. Yes, but not yet. Later, after we do Taylor series, we can worry about that.
Okay, so in the meantime, we can solve after parabolas.
Well, not necessarily. Sometimes, okay. Hey guys, I know it's a long session, but I mean, we can take a break if you all want. I've got the video happening here, so I kind of rather not, but can we go on? All right. Here's an example where a limit actually does exist, and you can prove it. The limit as xy goes to 0 of x squared y plus y squared over x plus root y. Now you have to be a little bit careful, because actually this could be 0. For example, if x is minus 1 and y is 1, then this could be 0. So you have to kind of make sure that x is not equal to minus root y. That's an illegal path, or any path that crosses that is no good. But given that, we ought to be able to factor this. If you notice that you can factor the top, maybe we can do something. You get y outside of x squared plus y over x plus root y. Well, this becomes a little bit suggestive. We've got something very similar to this up here, but not quite the same, so we can't actually factor it. But we do have a clever technique for dealing with square roots. Does anyone remember what it is? Multiply by the conjugate. So let's try multiplying by x minus root y over x minus root y and see what happens. Did I screw this up? I probably did. I probably did. Yes, I did. This was supposed to be a minus. I just wrote it down wrong. Sorry. So actually we could have factored it directly, but anyway, the trick is still good. I apologize for that. After you've done this, you get y, x squared minus y, x minus root y, over x squared minus y on the denominator. So that cancels that out. And now you can have no denominator, and you can just plug in 0, 0, 0, and that limit is 0. And if you try any path, you will find it's 0. But you cannot try every path as you had asked. So the previous method doesn't work. How do you know which one to do? Practice. Practice. I mean, I would say here, I was kind of a bit lazy. Maybe I should have just tried y equals 0 first and x equals 0 first. But if we did, we would be in good shape. Y equals 0, you can see the top is 0. X equals 0, you can see you get minus y squared over root y, which has a positive power of y, so that goes to 0. Then you could try a few paths. The question is, how do you distinguish between that example and this example? And there's no easy way. You kind of just have to get your hands dirty and try stuff. So that technique of multiplying by the conjugate, it's a good one. You could try that. You just got to have a bunch of techniques. And we're getting to the point in math where there's not always an obvious method. We've already seen some things like that. The more you go on, the more math courses you do, the more you'll see that you just often have no idea how to start, and you just have to try a few things, and hopefully something works. That's the way it is.
What do you think about this example? Why are you continuing to check now?
Well, indeed. I decided, why am I not continuing to check the paths? That's what I said. I probably should have checked them. As it happens, I knew how to solve this one because I wrote the problem, but also because I know that multiplying by a conjugate's a good idea. Here, I don't have a conjugate to try.
So every time we can multiply by a conjugate, every time we have a square root in the denominator...
You could try multiplying by a conjugate, and maybe it will work.
So what if we now take another line and get a different limit?
Well, indeed, you won't, because I didn't take a line. I just reduced it to something which I could plug in. Remember, I said if you can plug in and get an answer that doesn't have a 0 on the bottom, that's your limit. Okay. It works for any line. Okay? So I guess the point is that it's hard to distinguish between them, is what I'm trying to say. You can try different paths, and if you ever find two that are different, the limit does not exist. Or if you find that they're all the same, even if you've tried quadratic paths or something like that, then maybe that you can actually find the limit. Here's another example where you can find the limit.
In which case, how do you know you tried enough paths?
Indeed.
You can solve it in that manner.
Yes, to prove that there is a limit, it's not enough to just test a bunch of paths. That's right.
If you've done that on a test, would it even be necessary to test any path?
No, if you've done it, you don't have to test any paths. That's what I was trying to say, you know. But the best thing is to try some paths and then, or see, you know, it's like a string from two ends. You just don't know which one you're going to get there first. It's like trying to solve a maze backwards or forwards. You've got to just try things. Here's one which is from the book. They use epsilons and deltas, but I'll show you why you don't have to use either. Okay, this looks pretty similar to this one. It's 4xy squared over x squared plus y squared. The only difference really, essentially, is you don't have a fourth power on the bottom. Okay, sure, the x's and the y's are switched and you have a 4 and whatever. That limit you can do using the sandwich or squeeze principle. Okay, so here's another technique that you have up your sleeve. Look at this. Ignore this 4x for a moment and look at this quantity. Y squared over x squared plus y squared. What can you tell me about that quantity? How big could that possibly be? It's got to be less than or equal to 1, doesn't it? Because the bottom is bigger than the top. That's not true if you change, say, this to a y to the 4th, or in particular x to an x to the 4th. Actually, it is true with x as x to the 4th, but it's not true with the y, and that's the point. If I change this to y to the 4th, that's no longer true. Okay, so what? So what? It's also bigger than or equal to 0, because everything's positive. But we don't just have that, we have this. 4x times y squared over x squared plus y squared. How big could that be? Yeah, it cannot be more than 4x. But what if x is negative? That doesn't really make sense. Better put an absolute value. How small could this be? Bear in mind that this could be negative. So this is no more than 1. This could be minus 4 times something. Minus 4 times the absolute value of x. So there is a sandwich principle that also works for two variables. What is the limit as x, y goes to 0, 0, of 4 absolute value of x? Well, you just plug in 0. There's no y even. So that's 0. The same with minus 4x. So this is squished between two limits that go to 0. So you've got to write down some argument that this also has limit 0 by the sandwich principle. Because it's so similar to the previous things, I'm not writing it out, but you should write some sentences. Okay? So that's another technique that's different from the others. If you can see, this is a very common little thing to have a y squared over x squared plus y squared or something like that. The same thing would be, by the way, if you had a sine or something like that, you can use the sandwich principle. So clearly there's a lot more to be said about limits, because there's much more to be said about this course. In effect, we're doing 103 and 104 all in one semester and in multi-dimensions. You know, it's sort of just do practice problems, but don't try to learn more methods. Just be aware of the path, be aware of some sort of conjugate or just trying to factor, and then beware of a sandwich principle. If you have those three things, then you should just try each of them or any of them as your intuition leads you. And if you ever find two paths that are different, you're done. If you find a factorizing method, you could be done. Or if you, again, no hard and fast rules, just plenty of practice. All right. Any questions about limits? Yes?
The whole thing with the delta and the epsilon, we would only be if we weren't.
Well, the book, for example, uses the questions about deltas and epsilons. The book uses epsilons, deltas to do that exact problem that I just did in a few seconds with the sandwich principle. You can look in it. I mean, I've just taken it out of the book. But my feeling was that you ought to use the sandwich principle instead of the epsilon delta method. The fact is that this is a gray area in this course, right? Epsilon delta gives you the proper definition of limits, not just the path thing, but it actually really nails it down. My question is it examinable? I haven't seen exam questions that used it, but that doesn't mean it couldn't necessarily come up. The main thing is to ask your instructor, hey, could we have epsilons and deltas on the midterm? Now, I will be able to clarify that because I'm going to ask the course coordinator tomorrow morning, but I don't know the answer to this now. All right, I will try to communicate it with you. But if you really want to cover everything, you ask your instructor or the course coordinator, hey, is this considered fair game? That's my advice to you. Be communicative. I don't know the answers because I don't set these things. Sorry, but I will try to find out. Now, there's this concept of continuity, which is nothing more than a concept of limit combined with the notion, well, of what continuity actually is. So a function f is continuous at x0, y0 if the limit as xy goes to x0, y0 of f, and we've been doing these things the last half hour, that limit has to actually be the value of the function. That's what that means. So clearly the limit has to exist. This needs to exist. And, of course, the function needs to be defined as well. So in particular, this function here, this funky one, is not defined at the origin because you can't just plug in 0 there. it's defined everywhere else. Can it be defined at the origin in a way that makes it continuous? The answer is no, because the limit does not exist. This limit does not exist, as we found out. So f of x, y equals x squared y over x to the fourth plus y squared when x and y are not equal to 0, and some number, say q, when x equals y equals 0, this can never be continuous. This cannot be continuous, isn't continuous for any q, for any choice. So I'm trying to plug the hole. I have this hole there, and I cannot plug it because the limit as you go along different parabolas is different numbers. What would I plug it with? 0? A half? Minus a half? Can't do it. However, in this case, I could plug the hole at the origin with 0, and it would be continuous, at least as long as I avoided that bad path, x equals minus root y. So it's nothing more than a concept of, well, there's a limit. If the limit exists, then the function value there at that magical point has to be the same as the value of the limit. If the limit does not exist, it can't be continuous. So it's nothing more than limits combined with just the actual value of the point. So I don't want to spend much more time on it. On the other hand, I do want to move on to partial derivatives. So any other question about limits or continuity that's on your mind right now? Question?
Why is that considered continuous if you have that, like,
All right, so here, if I have this function, f of x, y equals x squared y minus y squared over x plus root y. And I want the domain to be x not equal to root y. Okay, so that's not allowed because the denominator would be 0. So that corresponds to something like minus root y has to be positive, so that corresponds to this not being allowed. Okay, so what I want to do is, actually, is it even all of that? X has to be negative, true, but y has to be positive. So it's even just, that's the bad bit here, that little part of the parabola on its side. What I want to do is define it at the origin as well in such a way that it becomes continuous on the domain, but without still not allowing that little bit, right? And I'm going to define it to be 0. I'm going to actually also set f being 0 if x equals y equals 0. So I'm going to just define it to be 0 at the origin. Now the limit along any path that doesn't touch this, that doesn't intersect this, will be 0. And if I also say that the function is 0 there, then its limit agrees with the function value, so it's continuous. So that's how you can have that. But there is this unfortunate subtlety of needing to dodge this curve like the plague. All right? Any other questions? All right, so let's do some derivatives. So we've done differentiation. The most naive derivative we can do is to fix y and let x be the derivative. So just consider this. Okay, it's not a very exciting function. If I graph z equals f of x, y, I get this paraboloid again. All right, let's just do this. df dx. Pretend y is constant. Well, how do I know y is constant? Maybe y depends on x. It shouldn't. But in order to really enforce that notion, let's, instead of writing a regular old d, we'll write the d in this form with the idea that it means partial. This is called partial.
How do I depend on the...
I don't know. You could have a curve on the parabola where the y, if you know what the x-coordinate is, you could have a curve on the paraboloid, rather, so that if you know what the x-coordinate is, then the y-coordinate is determined. In principle, it shouldn't.
Y and x.
Yeah, but not if I say take f of x comma 3x squared. Now y is a function of x, right? So, but I'm saying that in principle, yes, y should be independent. I'm going to write it in a slightly different way. This is the partial derivative of f with respect to x. And of course, there's a partial derivative with respect to y that's written df dy with the curly d's. And in this case, it would be 2y. So basically then, when I write df dx, I mean the derivative of f with respect to x, treating y as a constant. So for a more exotic example, if f of xy is x squared y cubed plus 3x plus 6, well then df dx partial is 2x times y cubed, y is a constant, plus 3, and the derivative of 6 is, of course, nothing. Whereas df dy, now I treat x as a constant, so it's 3y squared times x squared. Derivative of 3x with respect to y, if x is constant, that's 0. Same with the 6. So that's it, 3y squared x squared. This is not the same as implicit differentiation. In implicit differentiation, y was a function of x. This is back in Math 103 land, where you had to use a product rule on this and all that sort of stuff. Here, these partial derivatives treat one of the variables, in fact the other variable, as constant. Okay, now this can also be written as f subscript x, or f subscript y. That's a shorthand for the partial derivative. What does it mean? What does it mean? What are we doing here? What are we all doing here? Now, what are we doing with these partial derivatives? Here's what we're doing. We have some surface z equals f of xy in space, whatever it looks like. It's some surface, it's like a blanket, a Persian rug floating in the sky, ripply, whatever. All right. Here's a point where I want to take the derivative. If I slice along the line where y is constant, so this is supposed to be the x-axis, and this is supposed to be the y-axis. If I slice only along y equals constant, so that's a plane here, then the rug intersects this in some curve. df dx is the derivative of that curve. So all we're doing, basically, imagine that you're standing on this rug. Now, it would be nice if the rug was flat here, but you know, it could be on an angle and you might have to stand like that, or it could be curved and the tangent plane could be on an angle. But the point is, if you just face along the x direction, and to hell with y, then the surface of the rug is doing something, and all I'm doing is measuring the slope in that direction. I am completely ignoring the other direction. And I'm not only ignoring that direction, but every other direction. Just this way. And then the y derivative, of course, I'm turning around and I'm only looking at everything in this direction. So these are very feeble objects, these partial derivatives, in a way. They're throwing away most of the information. Technically, this is the limit, or at least evaluated at x0, y0, is the limit as h goes to 0 of f of x0 plus h comma y0 minus f of x0 y0 over h. I've kept y0 fixed, and I've only adjusted the x coordinate. And the similar thing for the y. So that y, of course, you put the y0 plus h. But that's the technical definition. In practice, we know that we don't do derivatives with these limits. We do derivatives using the product rules and the chain rules and all that sort of stuff that we've learnt. And of course it all works here because we're really only doing a regular derivative, keeping the other variable constant. All right, so I'm trying to give you a sense that this is a pretty weak sort of concept by itself and that it's not implicit differentiation. However, for all that, you may still have to do some implicit differentiation. Here's an example from a previous midterm. No, a quiz. It says we have a relation between x, y, and z. Log x plus y plus log x plus z plus log y plus... No. Log y plus z minus log x plus z equals 163. And it says z is to be considered as a function of x and y. So there you go. There's an example of this. I just declare that if you knew what x and y were, then you know what z is. So I'm considering this implicitly as defining a surface or some region in space. That's some surface-like thing, not necessarily a function, but some surface where z is given by this equation, if you know what x and y are. And you cannot solve this easily, perhaps, for z. Maybe you can, if you're clever. But nevertheless, the question is, what is dz dx? That's the question. What is dz dx at the point x, y, z? It doesn't actually say that. I'm going to tell you. That's the idea. What is dz dx? All right. So we have two free variables, x and y, but z depends on x and y. So we need a d dx. So I'm going to take d dx implicitly with respect to both sides of this equation. And this is no different to a Math 103 problem of implicit differentiation, other than that there's a y in there. But the y is constant. So pretend that the y is, say, 7. If you could do it in Math 103 with y being 7, and then just find d dx, then you can do it in Math 201. Okay, so you don't actually write 7, but you just think of it as like a 7. So what is the derivative of log of something? Well, it's 1 over that something times its own derivative. So if I differentiate this, I'm going to get 1 over x plus y times the derivative with respect to x of x plus y. And we'll worry about that later. The same thing with this. You get 1 over y plus z times the derivative of y plus z. Minus 1 over x plus z times the derivative. All these derivatives are partial derivatives with respect to x. Sorry about the handwriting there. Of x plus z. And that equals 163, right? No, we're differentiating both sides with respect to x. The derivative of 163 is 0, because it's a constant. Beware, that's a common trick. All right, now let's clean up. The derivative of x is 1. What's the derivative of y with respect to x? 0, because y is independent of x, and this is a partial derivative. So this is just 1 over x plus y. Plus 1 over y plus z times what? Well, the y derivative is 0, but the z derivative is dz dx. There's no way to simplify that, because z does depend on x and y, but z depends on x. And in fact, this is what we're trying to find. Similarly, here we will have 1 over x plus z times 1, that's the x derivative, plus dz dx. And that all equals 0. So now you just have to solve for dz dx. So what do you get? Well, the general aim is to expand this term and kind of factor everything that you can. So you get a 1 over x plus y, and then I see that this term over here, minus 1 over x plus z, And everything else, I can take a factor of dz dx, and I'll have a 1 over y plus z minus a 1 over x plus z. And so all you need to do, that equals 0, is solve for dz dx. And I guess you'd bring that over the other side and divide. So when you do this, there's a bit of sign flipping. And you get 1 over x plus z minus 1 over x plus y over 1 over y plus z minus 1 over x plus z. And maybe you can simplify that in some clever way by multiplying through, but that's basically it. That's basically it. All right, so again, it's just a regular implicit differentiation problem, but with this extra variable just in there to confuse you. All right, any questions about that? It's a good example. Make sure you can do things like that before the midterm. There's other examples from midterms, etc., etc. All right, so of course, if the function is of 3 variables instead, like w equals x, y, z or something, you can do a d dz as well. I only told you about df dx and df dy, but if f is of 3 variables, then df dz in that sort of case would be keeping x and y fixed and differentiating as in constant and differentiating. So I'm not going to comment on that further. It's just a different letter. So everything that works in 2 dimensions also works in 3 dimensions as far as this is concerned. Now, I do need to spend a little bit of time on some more theory. I mentioned that the derivatives that we just looked at, df dx and df dy, for a function of 2 variables, only tell you what's happening in 2 very specific directions. So it's possible that you could have these derivatives both existing, and yet the function might not even be continuous. Because remember, continuous meant that the paths from every direction have to be kind of nice in terms of limits. They don't have to have slopes, but they have to have limits. Paths coming to me have to have the same limit. And now I'm telling you that we just have derivatives that only care about the paths this way or the paths this way. So analogous to this, we kind of have to make derivatives along any path work. And it's not going to be good enough just to have the x and the y paths work. You need something more than that. So I do need to speak a little bit about this sort of thing. I mean, the classic example, as given in the book, is if you just let f of x, y, say, equal 1, what do they do? 1 or 0? Might as well be consistent. If you let it be equal to 1 when x equals 0 or y equals 0, and 0 otherwise, then you get this function. The graph of it is pretty boring. Here's the y-axis, here's the x-axis. Above these axes, it's 1. So it forms a little cross of height 1 parallel to the axes. But everywhere else, it's height 0, not on the axes. So the function's certainly not continuous at the origin, because if you go along either of these paths, any of these 4 paths, you have a height of 1, so the limit would be 1. Whereas if you go on any other path that avoids these lines, linear or quadratic or whatever, you could think 0 draws you always along the height 0. So the limit doesn't exist. The function's certainly not continuous, but its partial derivative is fine, because along the y direction, well, when y is constant, say along the x direction, the function's always 1. So it looks like f of x0 equals 1. So df dx at the origin is 0. It's flat going along this way. And the similar with the y direction. So that's a sort of technical example. It's kind of randomly concocted in a way, well, not randomly, but it's just to show you how weak this directional derivative stuff is, these partial derivatives. So let us be a little bit better, and we've got to just say what it means for a function to be differentiable in general. Now this becomes, again, of the technical sort of side. I don't want to spend too much time on it. I will have time to go on to the next section before we go. but I do need to tell you a little bit about it. So I want to have some notion that a function is differentiable. We said what continuous means. I want to say f is actually differentiable at x0, x0, y0. And again, the notion has got to be more than df dx and df dy exist. That's not good enough. I need to deal with every direction. So again, I don't want to get bogged down in the epsilon deltas. Here is an epsilon, but not delta thing. Here's what I need. I need to deal with this. Suppose we had a one-variable problem. You know that you want to look at the limit as of f of x plus h minus f of x over h as h goes to 0. And you want that to equal the derivative. So in some sense, what this means is you want that to be, at least you want this to exist. It doesn't even matter what it is. You want this to exist. Well, what does that actually mean? It basically means if we took, say, f of x plus h minus f of x, what would that look like? Well, it would look like approximately the derivative times h. That's sort of what it looks like. If it were actually equal to f prime of x, if the limit weren't true, then this would be an actual equality. So instead, I want this to be approximately equal to f prime x times h. So in order to make it actually equal to something, I'm going to say this is f of x minus f of x plus h minus f of x equals f prime x times h plus a remainder. And I'll call it epsilon times h, where epsilon goes to 0 as h goes to 0. That's what I need. I need this to be really small. Epsilon goes to 0 as h goes to 0. I'm going to try to rewrite this in a different way that doesn't involve a quotient. I've gotten rid of the quotient by this sort of stratagem. So I'm just going to replicate that and tell you what the definition is. But again, since it becomes more of a technical thing, I'm more interested in what it means. So here is the multi-dimensional version of this. F of xy is differentiable at x0, y0 means that the difference, and now I've got to call it delta x instead of h, because I've got a different h for y. I could have called them h and j or something, I guess. But anyway, the difference between this and this, f of x plus delta x, comma, f of y plus delta y. So here's xy, and here's a point very nearby, x plus delta x, y plus delta y. I'm now looking at the difference in the function values here and here, however high these things are. This has to be equal to the partial derivative in the x direction times delta x. So just pause and see that that's the analog of the derivative times h. H is like delta x. But I need to deal with the y direction as well, times delta y. And now I kind of need this extra bit. This would be approximately true, but I also need an epsilon 1 times delta x and an epsilon 2 times delta y, with the idea that these become really small. They kind of go away. So epsilon 1 and epsilon 2 go to 0 as delta x and delta y go to 0. So there's the limit. I kind of put the whole limit with any paths onto this epsilon 1 and epsilon 2. Okay? Again, it just basically means if I change x and y by a little bit, delta x and delta y, then the x direction changes by a multiple of the x derivative. The y thing changes by a multiple of the y derivative, however much you change it by, plus some other tiny little correction term. And when we do Taylor series in 2 dimensions, we will see more about how this is really like a square, and then there's a cube, and then there's a 4th power, and there are factorials and all that sort of stuff that we saw in 1 dimension as well. So, I kind of have to tell you this, but then I'm not really going to use it again. It's just important to see it. But as you know, I'm more interested in general in problem solving. Before I go on to sort of the problems, as it were, or the chain rules in particular, I do need to say one important thing about this. And that is this. It turns out f is differentiable at x0, y0 if the partial derivative in both the x and the y direction exist and are continuous, in fact, near x0 and y0. So what I mean is, here's my magic point. I want to consider the derivatives in the x and y direction there, but not just there, in a little neighborhood. So I want all of these derivatives. So every point has a little cross, the x and the y directions. And I want all of those derivatives to exist in both directions and be continuous in the sense that the x ones are close to each other and the y ones are close to each other. Then that's good enough for the function to be differentiable. Okay, so why do I not fall into the same trap as in this example here? Because the partial derivatives here are 0, but nearby they're not actually defined because they don't exist on this line here. So well, actually in this case the function is not continuous. So I also need, in fact, f to be continuous. So if all 3 of these things are continuous, then the derivative is going to exist. So this function actually violates the f by itself. So I need f and its partial derivatives. So I guess the idea I'm trying to emphasize is this. I said here the partial derivative only gives me information about that way and that way. But if I step over here and I get that information, then that kind of gives me some information about this way. Even though I'm only sort of sampling the information here and here and here, the fact that I'm doing it all around gives me a lot of information. And some of that had flipped right into it. So I just wanted you to have at least some intuitive idea. You can do second derivatives as well. So, for example, well, suppose that I have a function, I don't remember the exact one I wrote down before, but I'll write down something like this. F of xy is x squared y cubed plus 6x minus 3. That's close enough. So suppose I have this. Well, the first derivative with respect to x, the first partial, is 2x y cubed plus 6. And the first partial with respect to y, as we saw, is 3x squared y squared. How about the partial of x with respect to itself, so as in the second partial derivative? Well, again, you take this and you treat y as a constant and differentiate again. So the derivative there would be 2y cubed. Whereas if I took this one and differentiated with respect to y again, I get 6x squared y. The derivative of y squared is 2y. But because we've got 2 variables, we can actually do fx and y. Which order? I forgot to write it down. Most of the time it doesn't matter. But now I have to look it up. It is backwards, isn't it? You have to do y first. Yes? Good. Yes, so the best way to write it is d2f dx dy, which means that you're doing d dx of df dy. Good. So it means you have to do the y first and then the x. So if we take fy and then we do d dx of that. So we have to start with this. 3x squared y squared. And here you will get 6x y squared. So again, the idea is you take this, you differentiate with respect to y first, and then you differentiate with respect to x. But what if we did it the other way around? Fyx is equal to the derivative with respect to y of fx, which is, we take fx, which is 2xy cubed, and now differentiate that with respect to y, and you get 6xy squared. It's the same. We found that if you differentiate with respect to y first and then x, or x first and then y, you get the same answer.
When would you do that when you try to prove y?
Well, the question is, why do you even bother computing second derivatives? Why do you do second derivatives in the case of, say, one-dimensional functions? What were they good for? Do you remember? Can anyone tell me what second derivatives were good for in regular calculus? Acceleration is one thing, but even looking at graphs, what do they tell you about the graphs? Concavity. Same thing here. We're going to use all four of these second derivatives to work out concavity, whether you have a concave up, a concave down, or a saddle point, or all that sort of stuff. So it all comes down. And it also has an acceleration interpretation as well. So this is true for this case. And it turns out it's very, very often, but not always true, that it doesn't matter which order you do the derivative in, which explains why I couldn't even really remember what the notation meant. But I'm glad it meant what I thought that it meant. So here is another result. This is true if f, the first derivative in both, and all the second derivatives are continuous. Well, let's just say that. So if it turns out that everything is always continuous, no matter how you differentiate it, once or twice or 0 times, then it doesn't matter which order you do it. So for most of the functions we're interested in, as in any polynomial or most of the trig functions or basic exponentials, logs, wherever these things are defined, we know we can differentiate them over and over, and the derivatives are continuous. So most of the time for nice functions, this is true, in the sense that it doesn't matter if you do the x derivative first or the y derivative first. Either order will give you the same answer. Question?
Does it work the other way around?
Does it work the other way around?
If you find the mixed partial derivatives to be equivalent, can you then say that all functions were effective?
No, it doesn't work the other way around. The question was, if you happen to know that's true, do you know that all of these things are continuous? And I think that's not true. There are some weird counterexamples that you can make up. All right, what I'd like to do in the last few minutes is just give you a little introduction to the chain rule. I'll just give one introduction to it, and that will get us up to some sort of speed for this week. By the way, here's the map for the next 2 weeks. Next week, I'm going to try to get down most of the stuff that you need for the midterm. Maybe not quite all of it, but almost all of it. So that'll be the rest of chapter 14 and I guess a bit of 15. The week after is going to be a 4-hour mega marathon midterm madness review session. I'll have to tell you where the location is. It might be too small in here because I suspect the night before the midterm more people will want to come. So the point will be that the first 2 hours I will do a review of everything. And of course it'll be pretty quick. And some of it will be just summary. And then the next 2 hours will be problem session, question and answer. So you have to bring the problems, and I will do them. If no one brings problems, it'll be a very short problem session. So that's a little sneak preview. I'm going to send out an email about this anyway, but just so you know, the midterm's on the Wednesday in 2 weeks. So that means we have the night before. So here's the 2-minute flavor of the chain rule. I'm just going to give one version of it just so you can see it. Here, in multivariable calculus, we can have a function of any number of variables, normally 1, 2, or 3. And then the answer we've been giving is normally one variable. However, you can have a vector of functions. As we know, we've had these, a curve in space has one variable that's as its input, the parameter t, but it has 3 functions, the x function, the y function, and the z function. So we have to be able to deal with functions of different numbers of variables and also different numbers of functions coming out. The most simple example, in a way, is just this function of 2 variables here, where each of the functions is of one variable. So what I'm saying is, w, if I have any point in here, I know, in the plane rather, I know how high this w is. I know what the value is. But I'm not going to let x and y be any particular values. I'm actually going to put them on some curve. And so t tells me where I am at a time, and w might be how hot it is at any point in this space. I'm assuming the heat doesn't change. And what I'm interested in is how hot it is at different times as I move along. So I've reduced this function of 2 variables down to a function of 1 variable. So if x is a function of t and y is a function of t, then I could write w is f of x of t, comma y of t. But this means that w is a function of t. Okay, so it's just a regular old function, w of t. But you see how it's composed of a more complicated situation. If you know what t is, you have these 2 functions, x of t, y of t. So you compute them both. Then you plug into this function f of 2 variables, and you get back your answer. So you've sort of gone from 1 to 2 back to 1. So what's dw dt? It's a regular old derivative. The problem is, as I change t, x changes, and y changes, and f is sensitive to changes in both. And so the result will be sensitive to all of these changes. So basically, it turns out, the chain rule says that the sensitivity of f with respect to x is df dx. We have to multiply that by the magnification factor of how much x changes when t changes. So as t changes, x changes by how much? This times as much, dx dt. However, f then responds to that change by changing by df dx times as much. And this has to be partial because f depends on 2 variables, whereas x only depends on 1. That takes care of the x change. However, unfortunately, as it turns out, the y also has a sensitivity, so f cares when this one changes, and y also cares when t changes, so you end up with a parallel sort of term like this. And so that is a chain rule. It's a chain rule that covers this case, where one variable goes to 2, then back to 1. And so as an example, well, if f of xy is equal to, say, y e to the x, then, and w is equal to f of sine t cosine t, what is dw dt? I'll do this example and then I'll be done. So df dx, I treat y as a constant, and I'll just get y e to the x. df dy, I'm going to treat x as a constant, and then I'll just get e to the x, because e to the x is constant, and the derivative of y is just 1. So dw dt, just using the formula, is df dx, dx dt, plus df dy, dy dt, we've just computed that df dx is y e to the x. And then you need to differentiate x. So this is my x, and this is my y. So I need the derivative of sine t with respect to t. So this is going to be cosine t. That's the derivative of sine. Plus df dy is e to the x times the derivative of the cosine t, which is negative sine t. The answer, on the other hand, shouldn't have anything other than a t in it, because w is a function of t. So to get rid of this, I need to substitute x equals sine t and y as cosine t back into this. So this will be cosine t, e to the sine t, cosine t, plus e to the sine t times minus sine t. And you can simplify that a little bit into cosine squared t e to the sine t minus e to the t sine t. And before we finish, I want to point out that you could actually work out exactly what this is. You could work out that w is y e to the x. It's actually cosine t e to the sine t. And so you could have actually done this as a one-variable problem just with the chain rule and the product rule and check that you actually get that. So in fact, this is just the product rule in a way, combined with the chain rule. So at least it is in this case. So that's a little exercise to check that if you just differentiated that, you would get this. Anyway, next time we'll look at varieties of chain rules, and of course you'll see it if in class in any case.